Alright, so today I'm going to talk about the coolest formula in mathematics, my humble opinion. This is kind of like picking a favorite child. I mean, it's kind of hard to do, but this is a formula that I think is really cool. So to start off, we're going to start off with some preliminaries, just kind of basic stuff that you'll just need to know as we continue on talking about this or discussing this. So the first thing is an infinite series, denoted by the Greek letter sigma, is just adding an infinite set of numbers. So for example, if I have the infinite series from n equals 1 to infinity of the n, it just means that I'm adding 1 plus 2 plus 3 plus 4 and so on and so forth. We can use series to represent functions. This is what is known as a Taylor series. So for example, if I have the function e to the z, I can represent that by the series of numbers, the sum of n equals 0 to infinity of z to the n over n factorial, where n factorial is n times n minus 1 times n minus 2, all the way to 1. So for example, the first in that series of e to the z would be z to the first, or 1, and then the second one would be z to the first over 1 factorial of 1, and then z to the second, or z squared, over 2 factorial, which would be 2 times 1, or just 2, and so on and so forth. The sign of x can also be represented by the series. It's a little bit more of a complicated series. So we have the sum from n equals 0 to infinity of negative 1 to the n over 2n plus 1 factorial, all times x to the 2n plus 1. So just kind of give you an idea of how that series works. I have a couple example terms given there. So we have x, and then minus x to the third over 3 factorial, plus x to the fifth over 5 factorial, because of this negative 1 to the n here. You can also represent cosine of x. So the cosine of x is the sum from n equals 0 to infinity, negative 1 to the n over 2n factorial, all times x to the 2n. And again, some of the terms of that series are 1 minus x squared over 2 factorial, plus x to the fourth over 4 factorial, and so on and so forth. And then the last thing we need to know is just some things with complex numbers. So again, complex numbers are unreal numbers, are just where we represent them by the term I, where I equals the square root of negative 1. Since you can't ever have the square root of a negative number, because any number squared is positive. If I have negative 1 times negative 1, I end up with positive 1. And if I have 1 times 1, I also end up with positive 1. So we get around that by using these terms called I. So we have I equals square root of negative 1. I squared is just square root of negative 1 times square root of negative 1, or just negative 1. I to the third would be negative I to the fourth equals 1, and I to the fifth equals I, and we kind of continue on in that cycle. So to kind of give you an idea of how the series can be used to approximate certain functions, I have a graph here of the sine of x. So here we have pi here, and this is just a graph of sine of x. So next couple slides I'm going to show you what happens to this graph, or show you this graph along with the graph of some of the terms of the Taylor series of that function. So here we have the first term, where if you recall from a couple of slides ago, the first term of sine of x is just x. So here we have the graph of x, and here we have, so the red represents the graph of x, the blue represents x minus x to the third over 3 factorial, and then the green represents x minus x to the third over 3 factorial plus x to the fifth over 5 factorial. So that's just kind of to give you an idea of how we can approximate these functions, and as you add more and more terms, the graph looks closer and closer to the function until you add hypothetical infinity amount of terms where the graph is the function itself, where the graph of the series is the same as the graph of the function. All right, so now we're going to get to what's known as Euler's formula, which again is, in my opinion, one of the coolest formulas in mathematics. So let's just consider the expression e to the I theta. So applying the information from slide 2, where we had e to the z equals z, the sum of n equals 0 to infinity of z to the n over n factorial. We have e to the I theta. So instead of our z here, we have I theta. So we have I theta to the n over n factorial, and then we add up from n equals 0 to infinity. So the terms of that would be 1 plus I theta minus theta squared over 2 minus I theta to the third over 3 factorial plus theta to the fourth over 4 factorial, and so on and so forth. Also the cosine of theta, again from slide 2, we have 1 minus theta squared over 2 plus theta to the fourth over 4 factorial minus theta to the 6th over 6 factorial plus theta to the 8th over 8 factorial, and so on and so forth. And then I sine of theta equals I theta minus I theta to the third over 3 factorial plus I theta to the 5th over 5 factorial plus I theta to the 7th over 7 factorial, and so on and so forth. So you can see here the cosine of theta catches all the even terms in our e to the I theta, and then the I sine of theta catches all the odd terms. So we have I theta to the third over 3 factorial minus plus I theta to the 5th over 7 or 5 factorial, sorry, and then minus I theta to the 7th over 7 factorial. So from these results, we get the formula e to the I theta equals cosine of theta plus I sine of theta. And this is what is known as Euler's formula. Now, if we substitute pi for theta in that expression, we get e to the I pi equals cosine of pi plus I sine of pi. And the cosine of pi is 1, and the sine of pi is just 0. So you get e to the I pi equals 1. So e is an irrational number, so it just is a number that goes on infinite decimal places. And then if you raise that to a power of a non-real number, square root of -1, times another irrational number, which is pi, which is 3.14159.265, and so on and so forth, you end up with the nice answer of just 1, which I think was really cool. I'm not sure if you feel that way, but yeah, I just thought I'd spread that around. Again, this is, in my opinion, one of the coolest formulas of mathematics, so yeah. Thank you.